We are now going to talk about resistors in series. If you remember back to capacitors, we talked about capacitors in series and capacitors in parallel. The good news is that series and parallel mean the same thing. The bad news is the equations are actually the opposite of one another. So that's going to be confusing, but one, you have an equation sheet for tests, and two, we can actually think through what's going on. So pretty much the definition for our resistors being in series is that the same current goes through both of them. Whatever current gets to the first resistor leaves the first resistor and gets to the second resistor and then leaves the second resistor. The point being that there are no junctions in between. There can be junctions somewhere else, but we would at least refer to these two as being in series. So something to note is that you can have more than two resistors in series. So we could have 1, 2, 3, 4 resistors in series. But after that, if I have a junction and it splits, well, we would treat these as parallel and these in series. So do think about how you're trying to simplify this and don't start to say, well, hey, this one's in series with that. No, these are in parallel with each other, and you need to consider that first. But since there's no junctions here, these are all in series with each other. So if we want to make an equivalent resistor, what that means is I can replace these two resistors with one resistor. And the potential difference across that resistor will be the same as across both of these, and the current through each of these will be the same. So the nice thing is that we get to just add up all the resistances. So in the case here, since there are only two resistors, we get to just add the two resistances together. Now, the reason it's written this way is that you're allowed to have n resistors in series. That could be 3, 4, 5, 300. But remember that there can't be any junctions anywhere in there. So make sure that if you are trying to combine a bunch of resistors in series at once, that there's no junctions between any of those resistors. So again, this is not what the equation looked like for capacitors in series. But that's what it is for resistors in series. And you can actually derive this, as the book walks you through, using the relationship between potential difference, current, and resistance, using Ohm's law, and noting that the total potential difference here is simply the sum of the potential differences from the individual ones. So it's a little bit different when you do the capacitor derivation, because then you're thinking about potential difference and charge. So that's one way that this is different. So let's return to a scenario with light bulbs. And in this case, we have two different circuits, and each of these circuits has a battery in it, and they're identical batteries. So you can think of this as a 9-volt battery, a 6-volt battery, whatever you want, but it's the same battery. We then have three identical bulbs, and we're going to be able to model our bulbs as resistors. But note that one circuit, circuit 1, has one bulb in it. Circuit 2 has two bulbs in it. So we want to think through the brightness of these bulbs. And actually in a previous slide I talked about B and C having the same brightness because the same current passes through it. So really the question is, how do B and C compare to A? So let's think about this. We can apply the loop law for delta V, and we can actually do this for both circuits. So when I go through and do this, there's kind of two ways that you can think about this. Initially, you can just say, well, I have some delta V across A, and I have some delta V across B and C. Or you can start to say, hey, I'm going to model those bulbs as resistors, and I can talk about RA, RB, RC. However, what we know is that actually the resistance of all of these needs to be the same. We also know that we have the same current through bulbs B and C. Notice that I've called this current 1 and I've called that current 2. So again, in this case, we can say that it's actually just R. We don't have to have RA. We can just have total R. And that's because they're identical, right? If I told you they were totally different bulbs, then you couldn't actually assume that. So what we're trying to figure out is the brightness. Remember that the brightness is really based on the current. So if I call I2 equal to IBC, sorry for switching notations, we see that my EMF here is going to be equal to I2 times 2R. Well, so that just means that or IBC, that current is equal to my EMF divided by 2R, where in this first case, it's just the really simple Ohm's law version. So you see that the current in my second scenario, IBC or I2, is actually equal to IA divided by 2. This is a really important result. Now, to you might think, well, this is trivial, this is obvious. Great, you understand a lot about circuits. But let me pause and highlight a few things. Batteries have a fixed EMF, or fixed potential difference. Batteries do not have a fixed current. And this is a place where a lot of students get confused and make mistakes. So the thing that defines the current that comes out of the battery is the EMF of the battery and the load, whatever the battery is connected to. So we don't just say, oh, well, they're identical bulbs and it's identical batteries, so the light bulbs are all the same brightness. No, that once you have two bulbs in series, you actually have a greater resistance. So that's like holding a hose closed. You make it harder for the water to flow. So we actually have half of the current now flowing through both bulbs. And so that means that you have half the brightness. And again, another way to think about it is that this delta V in magnitude must just be equal to your EMF. Well, here, each delta V, again in magnitude, because depending on how you think about it, it's negative, is equal to EMF over 2. So that's another way to think about this, and then you would have half the potential difference across the bulb, the same resistance in the bulb, so therefore less current. So there's a couple different ways to analyze this, but in either scenario, you get the idea that the bulbs in the series case are less bright. So please be careful about this. Identical batteries means identical EMF, not identical output current.